So today we're going to be talking about Rayleighs criterion, but before we can talk about it and really understand it, we first have to understand what diffraction and resolution are. So diffraction is the bending of a wave around the edges of an opening or an obstacle, and it occurs with all waves. So remember that light is a wave, so we can apply this to how light will react when it hits an obstacle. So in these pictures, we see that the waves, as they come in contact with an obstacle or an opening, then they begin to bend and change shape. And they do this according to the size of the opening. So you see this here, they're bigger, and this here, they're smaller. And so it just affects the way that the wave bends. So on this slide, you see that we have two different graphs, and they both represent the varying intensities of two different waves. So on the wave on the left, we see that this is what happens when a wave comes in contact with a single slit. So there's one opening, and that's kind of the example of what we saw in the previous slide. And then on the right, we have a wave that comes in contact with two slits, and so there's two openings, and so it creates this kind of a function. And so on the bottom here, this is what we call diffraction patterns, and these patterns can be compared to the waves that they represent. So for example, this diffraction on the bottom is representative of this single slit wave, and this top one is representative of the double slit wave. And so here you'll see that the waves are most intense at the central maxima, or at this center part. So this graph is representative of what happens when a light goes through a circular aperture or a circular lens. So you'll see that the wave is the most intense again in the middle, and then as it spreads out, the intensity decreases or it fades. And so this is essentially a ripple effect, so like when you throw a rock out onto a lake. And so that is circular diffraction. And so the next term that we want to review real quick is resolution. Resolution really simply is like the ability of a lens to produce sharp images. And so for example, you'll see that on the right there's a high resolution image of a sheep, and on the left is a low resolution of the sheep. In terms of light in images, resolution explains how sharply we can distinguish two separate light sources. So on this slide we have three different images of two light sources interacting with each other. And in the most right image, we can see that the light sources are separate. We can tell that there's two. And so we say that the images are well resolved. This compares with this middle one, because with this middle one you can just barely tell that it's two light sources, and so we call this just resolved. And in this right image, you're unable to distinguish the fact that there are two light sources, and so we call this unresolved. And on the bottom here are graphs that represent the waves in the images above them. So this graph shows the waves of each individual light source and how they interact with each other. And this kind of begins to open up the discussion to what we're mainly here to talk about, which is Rayleighs criterion. And so finally getting to Rayleighs criterion, this criterion basically says that there is a calculatable limit to when two images become just resolvable, or when they just become barely distinguishable from one another. So when you graph the two waves, the images become just resolvable when the maximum of one wave is directly over the minimum of the other. So here again, maximum of one wave is directly over the minimum of another. And so as I said, Rayleighs criterion is a calculable limit. And so this limit is determined using your theta, your wavelength, and the diameter of your aperture lens. And so your angular separation is the angle that's created between your two light sources and your observer. So again, this is the theta. So Rayleighs criterion says that two images are just resolved when the angle between those two images and the observer is equal to 1.22 times the wavelength divided by the diameter of the aperture lens. In other words, just roughly from this, we know that angular separation, it's going to increase as the observer gets closer to the objects. And so, of course, if you have this observer that gets closer to the objects, the angle of separation is going to increase. And as you get farther and farther away, like let's say the observer is going to be over here, then the angle of separation is actually decreasing. And so, using this formula, we can see then that we know that the greater the diameter of the aperture lens, so the more light that can enter the lens, or maybe like the bigger the eyes are, the smaller the theta needs to be. So in other words, the farther the object can be. And so this example can be really apparent when we think of a car driving towards us at night. So let's say, imagine that you're on a dark road and for some reason you're just standing still in the middle of the road. So eventually you see that a light is approaching you from a certain distance, and so it looks like a single light, and so you'll probably think to myself, oh, this is probably just a motorcycle, how cool. But then as a light approaches, you actually recognize that it's two headlights, and so it's actually a car. Let's just imagine there's a car right here. And so it is when you begin to recognize that there are two lights that Rayleighs criterion has been met. And so let's compare that to this image. So we have two headlights, and here's this theta, and it's when this theta is equal to, again, we have theta is equal to 1.22 times wavelength over d. So it's when this criterion is met that we begin to see the two headlights. And we begin to recognize that it's a car. So now, for a real-life example, imagine that you are on a spaceship and you're looking out the window. So you know that you are approaching two stars, but right now you can only see one. Assume that the lens of your eye has a diameter of 10 millimeters and the wavelength of the star's light is 350 nanometers. So, at what angular separation will you begin to see two stars that are just resolvable? So for this problem, we can obviously use Rayleighs criterion. So knowing that we're solving for theta, we can just plug in lambda and diameter. So knowing that we're solving for theta, we have the lambda and the diameter. We can do that 1.22, which is constant, times lambda, which is 350 nanometers. We can go ahead and change this into meters, so we'll do times 350 e to the negative 9th meter divided by the diameter, which is, so the diameter of your lens, which is 10 millimeters. So that is equal to 10 e to the negative 3 meters. And meters will cancel out. So putting all of that into the calculator, you get that theta is equal to 4.27 e to the negative 5ths. And the units for this will be in radians. So applying all this, we know that when theta is equal to 4.27 e to the negative 5th radians, that is the moment when you begin to see that there are two stars instead of just the one.